All right, so let's start this problem. Again, we're trying to draw the shear force and bending moment diagrams for this. This is problem 433 out of the book. So let's start by finding our reactions. So I'm going to have AY and AX, two forces at my pin, and at this roller, I'm going to call that BY. So I want to find those reactions first. So I'll come over here and I'll draw a free body diagram of this structure. So I know here on the end I have a 20 kilonewton force and I have an applied moment at the end of 150 kilonewton meters. And then I have this distributed force, uniformly distributed, constant. And it is 40 kilonewtons per meter. Oops, I broke 3. Sorry. This section is 3 meters. This section is 8. And I'll go ahead and redraw my 3 unknowns for the reactions. Now it's convenient, and usually as part of the first step, is to go ahead and resolve this distributed load into a concentrated force that's equivalent. So to find the value of the force, we want the area under the curve, which is 40 times 8. Right? So that's 320 kilonewtons. And the distance, the centroid, will be half the distance, so that'll be 4 meters. So with that, we have all of our things, or components that we need to find the reaction. So I'll start by summing my moments about the pin at A and making sure they're in equilibrium. So I've got a lot of stuff going on here. So let's start, we'll go over on the left side and we'll work to the right. So this 320 kilonewton force is going to create, according to my sign convention, negative moment at a moment arm of 4 meters. Everybody see that? I go all the way out here on the end. I've got that 20 kilonewton force, also negative moment, and that moment arm will be 11. Then I've got this moment sitting out here, which is also negative. And then the unknown Y reaction, which is the only positive moment in this system, and it has a moment arm of 8. So the only unknown we have here is BY. I want to trust you guys to give me the value.
113.75.
113.75. Does that sound familiar? So then we would sum forces in the Y direction to find AY. So I have AY is acting up, BY is acting up. My concentrated equivalent force, the 320 kilonewtons, is down. And then way out there on the end, the other 20 kilonewtons. Did I forget anything? I think that's it. So we should be able to find AY
226.25.
226.25. That seems reasonable. Ms. Holland, does that help you?
Yes.
Did you get those numbers by any chance?
Yes.
Okay.
I do admit, I looked at the solution manual and it was just numbers different, and I didn't know if I was missing something or if I needed to add something, but those numbers are right.
Okay. Does the back of the book have different? Oh, I guess it doesn't have them in the back.
Yeah, it was 33.75. And then AY was 206.2.
Oh, really?
That's what I got too. That's what I got.
Yeah. So what did I do wrong?
They didn't put
That
it
math is
into
right.
When I do that,
Doesn't matter.
That's right. What you wrote down. But BY is 206.25.
Okay. Okay, let's start again. Is BY right?
BY is 206.
BY is 206.
Yeah.
It wasn't 113.75. Oh.
Well, start up again. That's what I got on my I mean.
Okay, so let's cross that out. So if you calculate this equation, you get
206.15.
okay. And I guess then when you redo this one, you don't get that, right? What do you get?
133.7.
And that's what's in the back of the book? Well, that's good. So, Mr. Province, you're the one who messed up.
I mean, I was just going off of somebody's homework. That's what I was
Oh, whose homework is that? We won't say.
We won't say.
Oh, it's Mrs. Holland's homework.
Yeah.
Oh, that's interesting. Okay. Well, I guess hopefully that's right. Would somebody check that before we move on?
I did.
Okay.
That's right.
Anybody else get a verification? Okay, I got more than one person got those numbers? Okay, cool. That would have been a little troublesome. Okay. Make it a little cleaner for me now. I'm gonna cover that up. Well, I'm not gonna do it just yet. All right, let's see. You get it now? Okay. So let's go ahead now and start our template. So I know I'm going to start here. There's a reaction, so I'm going to have something happen in there. Then there's the end of my beam. So this looks like a good place to start. And my values are going to be in kilonewtons. Okay, so what's the shear at A? Well, it would be AY, and we found AY to be 133.75. And that's positive or negative shear?
Positive.
Positive. So we'll start here at 133.75. What's the shear over here at the free end?
206.
No.
No.
With that applied load right at the end, what is the shear going to be? Think about a little free body diagram of that chunk of the beam. A little DX chunk with your 20 kilonewton force here. Now on this face, what's positive shear? Up or down? Up. So you can see those two forces balance. So we're going to have a positive shear at the end of 20.
Oh, that's right.
You see that?
Yes.
So that means when we get down over here, we better hit 20. So let's see if it's going to work. I'm going to kind of draw a little line here to kind of delineate that from what I'm going to do next. So I know it's not next to the graph, but if you follow down to this part, you'll see that the change in shear is the area under the load diagram. That's what we're going to do first. So what is the change in shear from A to B? Should be the area under the load diagram, and that is 320, and it's negative. So what's 133.75 minus 320?
186.25.
Negative 186.25. Okay? Now, our corollary to this is that the slope of the shear diagram is equal to the load. So what's our load? Let's go up here and see. Our load is negative 40, negative 40, negative 40, negative 40. It's constant and negative. So here's a constant negative slope. In fact, if I actually looked at that, it would be negative 40 to 1. There's my shear diagram.
So it doesn't necessarily pass through the center.
Never. Well, not never. It doesn't. I like your first thing. I'll rewind. Okay, I'm erasing this later. It doesn't necessarily pass through the center.
So why
It passes through wherever it passes through. And you can always find that point. And we're going to do that right now.
So you don't have to do
You don't have to do what?
where it passes?
Oh, you do have to.
don't know how we missed that.
I'm going to call this point 1.
I didn't do that on the homework.
And that actually shows me an important place, because what's going to happen here in the moment diagram? Since the shear is 0, the moment's going to be a crest or a trough. It's going to be a max or a min. We'll have to see which one it is. Probably a min. I mean a max. I'm sorry. So how do I find x1?
133.75 divided by 40.
We're going to start with what? Change in shear. What is the change in shear over this distance? You start at 133.75 and you go to 0, so the change in shear is negative 133.75. What is the area under the diagram? If I project this up and look at this area for x1, what is that area? 40 times x1. Remember, 40 is negative. Negative 40 times x1. So therefore, x1 is 133.75 divided by 40. 3.34 meters. So I'll go ahead and pencil that in. So if this is 3.34 meters, what's this distance over here? 8 minus that, right? So that's 4.66. Now I'll return to my shear diagram. So, what's the change in shear from B to the free end? Well, according to this, I forgot something. What did I forget? As I go from the left side of BY to the right side of BY, I have to account for the change in shear being equal to BY. BY is up, and it's equal to... So what is 186.25 plus that? It comes out to be 20. Hey, I like that. So the change in shear between here and here is the area under the load curve, and the load curve is 0. So it matches. Yay. The slope of that is equal to the load, and the load is 0. So I get a horizontal line. There we go. So there's my shear diagram. So what's the maximum shear in the beam? 186.25. And it occurs just to the left of B.
Even though it's negative, it's still a max.
Well, the sign just tells you the direction. It's still 186.25 kilonewtons. And whether it shears up or shears down, your material still fills it. You still need to know the max. All right, let's put all this together now and figure out what our moment diagram looks like. So I'll assume positive axis for both direction and moment, and all of our values will be kilonewton meters. Do we know something about the moment? What's the moment at A? It's 0. Now this is a tricky one to remember. The moment at B is not 0. You only get these 0 moments at connections when they're on the exteriors. This is an interior support. It will not be 0. What's the moment at the free end? What kind of bending moment is that? Positive or negative? Negative. So that should hit 150. I'm not too negative 150. I'm trying to figure out what the scale of this thing's going to be. I'll just put it here, minus 150. Okay, so now we know that. We're ready to roll. We know from our relationships that the change in moment is the area under the shear diagram, and that the derivative of the moment is the shear. So let's apply that. So the change in moment from 0 to 3.33 meters over is the area under this part of the curve, which looks to me positive. and it's going to be 1/2, it's triangle, so 1/2 base times height. 223.4. Does anybody else get that? Just to check. Sounds reasonable. Yes?
Yeah.
So 223.4. Okay, now what's the shape of the curve? Well, the shape of the moment diagram is given by the shear. So you start here at the left side, you go up and you see the shear is a big positive number. So I'll draw a big positive number. And it decreases to 0. If I did this one, you could see it's a 133.7 up for every one. So I should be able to connect those two and get my curve. So, constant curve, integrate it once, get a linear curve, first order, integrate that, get a parabolic shape. Alright, here we go. Change in moment now is area of the shear diagram. If we go from this point, we're at 0 at 3.34 to 8, what's this area? Well, that's a negative area. So what's that value? It'd be 4.66 times 186.25 divided by 2.
Or negative 433.96.
433.96. Anybody else get that? Now we're going to subtract that from 223.4. So what's that?
Negative 210.6.
You guys got 210?
Yeah.
Looks like I'm going to adjust my thing here. So let's see. This is 210's about right here. So negative, what'd you say, 210? 210.6?
We're subtracting what? 186?
No, well, the amount we're subtracting is the area of this part of the curve. And since it's a triangle, it would be 1/2 base, 4.66 times height, negative 186.25. So the moment, the slope of the moment diagram is the shear. So we look up here, the shear is still 0, and then it gets to a really large value. So I'll draw that. So over here, this slope is minus 186.25. Sorry, I've got kind of small there. So now if you connect those from 0 slope to this big negative slope, you get something like that. So now the change in moment over the last 3 meters should be the area of the shear diagram, which is 20 times 3, which is 60. That's plus. So what's negative 210.6 plus 60?
Negative 150.
Pretty close to 150. We lost some stuff along the way, it looks like, right? That's okay. That's not a killer. So that's okay. So what's the slope of that part of the diagram?
Straight line.
Yeah, you go up here and you see the slope is constant and positive. So if we looked at that, that would be 1 to 20. So there's your moment diagram. So what's the maximum moment? 223.4. Now if you were making a concrete beam, you would have to worry about the maximum positive moment and the maximum negative moment. And you have to design your beam to handle both of those. Steel, you don't have to worry about it. You just design it for the maximum moment. It'll handle it both in compression and tension equally. In reinforced concrete, obviously, we'd have a lot of reinforcing steel in the bottom of the beam here with positive moment. And then you see over the support, you'll look up here that this part of the beam was going to really bend down. So you'd have tension in the top of the structure. So you'd have to design it for what's called compression steel, but it's actually in tension at that point. Any questions before I turn this one off? That was a good one. I like that one. Did you guys like that one when you worked it?
Yes.
This is a very doable homework problem.
Test problem?
I'm sorry, test problem.
Yeah, we tried.